Hi everybody! So in today's video we're going to be thinking about the calculus concept of continuity. What you really need to know about continuity is that being continuous means that the graph is connected. So I like to remember that because they both start with the three letters C-O-N. But basically you need to just know that if I say that a function is continuous, it means everything everywhere is connected. Now there are three pieces to continuity that we examine in order to determine whether a graph is connected or not. We want to make sure that the limit as x approaches whatever number we're looking at from the left for our function is equal to the limit as x approaches whatever number we're looking at from the right for our function, which has to be equal to the actual function value. We kind of went through why those three ideas are really important in the activity we did today in class, but that's the technical definition of continuity, is that the limit from the left has to equal the limit from the right, which has to equal the function value. Now, since not every function is continuous, we say that if a function has a place where it is not continuous, that it has a discontinuity at that location. A discontinuity is just a place where the graph is disconnected at that x value. For example, on this graph, we can see that there would be a discontinuity at x sub 0 because the graph is not connected at that place. There's an open circle, and then there's a closed circle. So the graph is not all connected to each other there. So the discontinuity would be located at x equals x sub 0, which is what we're calling that specific x value. And if I said, what are the intervals where this graph is continuous? So this is where I'm disconnected. Where are you connected? We would use interval notation to explain that. So we would say that we are connected from negative infinity through x sub 0. And I'm making those open brackets because I'm not including the endpoints here. I can't include negative infinity because it's not possible. And I'm not including x sub 0 because I'm not continuous there. And then I would say union, and then I would say x sub 0 through infinity. Now these are intervals, not ordered pairs. So we're not talking about a specific ordered pair. We're giving intervals where we are continuous. So I'm continuous for all of these x values and for all of these x values. Now there are different types of discontinuities, and one of the things we're going to need to be able to do is to classify discontinuities that we see by the type that we see. A jump discontinuity is when two sides of the graph do not connect to each other. You see this a lot with piecewise functions. A lot of times they will have jumps at the breaking point. Now we would say, if we were asked to explain why the function was discontinuous here, it would be because the limit from the left and the limit from the right are two different values. So we would say because the limit as x approaches, in this case c, from the left does not equal the limit as x approaches c from the right. An infinite discontinuity is just another name for an asymptote. And we call this an infinite discontinuity because the values, the y values on the graph, become infinitely large. They go up towards infinity or down towards negative infinity. We see these a lot with rational functions. Not always, but a lot of the time, rational functions will have infinite discontinuities, asymptotes somewhere. Now in this case, the limit from the left and the limit from the right would be the same. So we wouldn't be able to explain our answer the same way because the limits do match. They're both going to positive infinity. The difference here is that the function value, the actual y value of the function, is undefined. So we would say here that the limit as x approaches our c value, let's call this c, of f of x does not equal f of c, the actual y value. So you'll notice here I didn't list the two limits separately. I used a two-sided limit here because the two sides do match, but I'm just saying it doesn't match the y value because you're never going to touch that asymptote. You're never actually going to have a y value here. Next, we have something called a removable discontinuity. A removable means that there's a hole in the graph. Sometimes there's a hole like this one where there's a closed circle somewhere else, and sometimes there's a hole like this one where there isn't a closed circle somewhere else. But it doesn't matter. It's called a removable discontinuity. The reason we don't call it a jump is that there isn't another piece that we're connecting to. It's all part of the same continuous kind of slope here, kind of curve. The only difference is that there's one point missing from that curve. So we see these a lot again with rational functions. Now in this case, once again, the limit does exist. The limit from the left and the limit from the right are pointing to the same place. The problem is that again, the actual y value is somewhere else. It's not in the same place as where those two limits are pointing to. So once again, we would justify this by saying that the limit as x approaches c, and again I'm using a two-sided limit here, does not equal the function value at c. Finally, we have something called an oscillating discontinuity. Now these come up very rarely. They come up specifically with trigonometric functions. You will not see these in function form very often where they give you an equation, but you will see them on graphs pretty regularly. What's happening here is that this trigonometric function is changing between high and low so fast that the two limits on the two sides never meet. So we would say that the limit as x is approaching, in this case 0 seems to be where our discontinuity is, 0 from the left does not equal the limit as x is approaching 0 from the right. Now, what are you going to be expected to do with this information? Well, an example of the type of question you might be asked is this. Given this following graph, locate and classify the discontinuities, then list the intervals where the function is continuous. So, on this first graph, if I just sort of start on the left side of the graph and I follow it along until I find the first discontinuity, the first discontinuity would be at x equals -1. And I would classify this as a jump discontinuity. And if needed, I could explain that by saying that the limit as x approaches -1 from the left does not equal the limit as x approaches -1 from the right. Because if you look at this graph, from the left, my function is approaching +3, and from the right, my function is approaching -1, close to that x value. The next discontinuity that I see happens to be at 0. It looks like the graph is sort of approaching an asymptote, some sort of like infinite asymptote from the left, and this open circle from the right. So I would say my next discontinuity would be at x equals 0. I would call that an infinite discontinuity because one side of this graph is approaching infinity. I'm never going to be able to jump between 2 points here because I'm never going to touch another point going up this way. Which is why I'm not going to call it a jump, and I'm not going to call it removable because it's not a function that's connected without that one point. It would never be connected. If I needed to explain this, I would say it's because the limit as x is approaching 0 from the left does not equal the limit as x is approaching 0 from the right, which also does not equal the function value at 0, which doesn't have a closed circle anywhere. I couldn't include this part, the function value there, for the first part, for the jump, because there is a closed circle here. So one of these limits does equal the function value, but the other one doesn't. The next discontinuity that I see is at x equals 1. Now x equals 1 would be an example of a removable discontinuity, because with the exception of that one point, this graph is actually connected. And we would say that it's a removable discontinuity, and the limit, which does exist because the left and the right are both approaching the same value of f of x, does not equal the function value f of 1, which is the part that's in a different place on the graph. Now, if I needed to list where I am continuous, I'm going to be continuous everywhere where there isn't a discontinuity. So I would be continuous from negative infinity to negative 1. That's this first section of the graph here. And I'm going to make that a closed bracket on the negative 1 since I actually am connected to that closed circle. Then I would be continuous from negative 1 to 0. And I'm making both of those open parentheses because this is an open circle and I'm never actually going to touch a point when x is 0. Then I would be continuously connected from 0 to 1. And I'm making both of those open because both of these are open circles. And finally, I would be continuously connected from 1 to infinity. And I'm making this 1 open because, again, open circle there. We're not including that point. And then I would just put my union symbol in between each of these intervals. For number 2, if I was looking for my discontinuities, my first discontinuity that I noticed on this graph was at x equals negative 3. I would classify that as a jump discontinuity, and I would say that it's a discontinuity because the limit as x approaches negative 3 from the left does not equal the limit as x approaches negative 3 from the right. Now I would not write this does not equal f of negative 3 for this example because one of the sides of these limits, one of the sides of this piece does equal f of negative 3. There's a closed circle there. So I can't say does not equal f of negative 3. My next discontinuity, it looks like there's an asymptote here at negative 1. I see a dotted line. So because it's an asymptote, I would call this an infinite discontinuity. Now, I can see that both sides are going up, so both sides are approaching infinity here. The problem is going to be we're never going to have an actual value at that asymptote. There's never going to be a function value. So I'm going to use a two-sided limit that the limit as x approaches negative 1 of f of x does not equal the actual value at negative 1. And finally, the last discontinuity that I see is at x equals 2. It looks like there's a hole in the graph, which we call a removable discontinuity. So I would say x equals 2 is a removable discontinuity. Now the two-sided limit here does exist. The left and the right do match, but the limit as x approaches 2 does not equal the actual function value at 2. If I now needed to list my intervals of continuity, I would be continuous from negative infinity to negative 3. And that's an open bracket on the negative 3 because that's an open circle. Then I would be continuous from negative 3 to negative 1. And I'm going to make it closed on the negative 3 and open on the negative 1 because this is a closed circle and this is an asymptote, so I'm never actually going to touch that number. Then I would be continuous from negative 1 to 2. And I'm making both of those open because I'm never going to touch this asymptote, and then I have an open circle here where I'm not connected. And finally, I would be continuous from 2 to infinity, and I'm making the 2 an open bracket because I'm not actually going to be able to touch the 2. There's an open circle there. All right, that is the big idea of continuity. Continuity just means connected. We can use limits as the technical definition to talk about it, and we can classify it using different types of terminology. Thank you guys so much for watching. Have an awesome afternoon.